Hi and welcome to the second video on Topic 3, Unit 4, Mathematical Methods, Discrete Random Variables, which will lead to the Bernoulli distribution and binomial distributions a little bit later on. Now this topic is going to be a bit more new content, and it's based on our work from 14D. So I'm going to talk to you about the expected value, variance, and standard deviation of a discrete random variable or a discrete distribution. So there's a couple of definitions first of all, and that is that the expected x, the expected value of x, that's just another way of saying the mean. And I'll add to that, which you'll see. In this instance, we usually write mu, which is like a U with an elongated stick at the front. Mu, the Greek letter, as our mean. But you might still see x bar pop up from time to time. The variance x is the variance of x, my apologies, but that's how we write it, var x. And the standard deviation of x is written standard deviation of x, but the standard deviation of x is the square root of the variance. So both of these are measures of spread. Whereas the mean, mu, or the expected value of x, is a measure of where the center is. So let's talk first of all about the expected value, and this one's a bit easier. Take a common dice roll. X is the outcome when the dice is rolled, and so this is what could happen, 1, 2, 3, 4, 5, 6, and here's the probabilities of those things. They all have a probability of a sixth. We would expect that our overall average, and this won't happen for 2 dice rolls or 3 dice rolls, but if we roll the dice 1,000 times or 1,000,000 times, our overall average should be that we get a fairly even distribution of 1s, 2s, 3s, 4s, 5s, and 6s. So the overall average should be the average of 1, 2, 3, 4, 5, 6. Now, it's not that simple for discrete distributions, because if we change, let's say 6 was more likely, then our overall average should drag up slightly. And I'm going to show you how to do this calculation. But we would expect to get something in the middle, which would be 3.5. The median of this set of data, 1, 2, 3, 4, 5, 6, is 3.5. In fact, the expected value of x is 3.5, and this is the formula that you'll use to calculate the expected value of x. So be aware of that formula and use it as you're going forward. Let's confirm it for this particular instance. So I know x, I know the probability of x, I want the sum of x times the probability of x. So 1 times 1/6 is 1/6, 2 times 1/6 is 2/6, 3 times 1/6 is 3/6, 4 times 1/6 is 4/6, 5/6, and 6/6. Now you might be inclined to simplify these fractions. Definitely 1, 2, 3, 4 can be simplified, but I need to do the sum. So I'm not actually going to simplify them, because they're easy to add together if I've got the same denominator. And this probability x equals x. This is x is the variable, little x represents all my possible outcomes. So it's basically saying sum up if x is 1, and if x is 2, and if x is 3, etc. So we've done our x times the probability of x equals x, so we now add all those together. 1/6 plus 2/6 plus 3/6 plus 4/6, 5/6 plus 6/6. You probably don't need to write this line of working down, but my total sum is 1 plus 2 plus 3 plus 4 plus 5 plus 6 is 21 over 6, which equals 3.5 as expected. So that's an expected value of x, but this is a discrete distribution that is called a uniform distribution, because all the probabilities are the same outcome, and all the outcomes have the same probability. My apologies. Let's have a look at example 2 where that's not the case. In a fair game, I get to choose 1 cup. The following prizes exist under the cups. So if I have, there's 7 cups with nothing underneath them, 2 cups with $2 underneath them, 1 cup with $5. So then let's determine what is this in terms of x and the probability of x. So first of all, x in this case is the prize. I want to know how much I'm going to win. That's the most important thing. So my little x will be the prizes I can get. I could get $5, I could get $2, or I could get nothing. And then the big X could equal one of those three x's. But I want to work out what the probability that x equals little x. Well, the probability that x equals 5, well, there's only one cup out of 10. So it's 1/10. That's a 6, sorry. 1/10. The probability that x is equal to 2, there's 2 cups with $2, so that's 2/10. And the probability that x is equal to 0 is 7 cups, which is 7/10. And you see my probabilities add up to 1 now. I can now work out my expected winning. X times the probability of x equals x in each instance. I get 5/10, I get 4/10, and I get 0, because 0 times 7/10 is 0. And therefore, my expected x is equal to 9/10. And 9/10, of course, is, in this instance, because of the context, going to be 90 cents. So that's a really interesting result. And it reminds us that this expected value might not actually be a value that we can get. What it's saying is that over time, you play this game 100 times, on average you can expect to get about 90 cents per game. You'll never actually get 90 cents per game, but you might get 0, 0, 0, 5, 2, 0, 2, 0, 0, 0, etc. Over time, your average will be 0.9 or 90 cents. And that's how the game works, and that's how expected values work. So there's our work on expected values. And I might carry on and just talk to you about variance, but this is a little bit trickier and it's going to take a little bit longer, so you'll need to be patient. So here we go. For standard discrete distribution, let's talk about the variance and the standard deviation. So we can take that common dice roll. Again, the same as before. The outcomes are 1, 2, 3, 4, 5, 6, and the probabilities are all uniform at 1/6. Here's a little bit of an example here of what might happen. I just made these numbers up, but you can see a dice roll is unpredictable and you could get anything. Now, we know that over time, our mean, which is x bar or mu, should be equal to about 3.5. We did that calculation earlier. This was our expected x value. What we don't know is the standard deviation of the variance. So here's our standard deviation and variance formulas, the ones that you've probably seen before, you're most used to, and they're the ones that you will see if you look it up. We could calculate these if we actually have a set of data. That set of data there, we can work out x, we can subtract the mean, work out the mean of it, subtract the mean, square, sum the squares, divide by how many numbers are, take the square root. But we can't do this theoretically for a discrete distribution. We want to know what happens if you play 1,000, a million, an infinite number of times. What is the measure of spread likely to tend towards? So, and that's what we've got here. What do we expect? So we're actually going to build a different way of viewing this. Let's have a look. So consider this. E of x is the mean mu. And that means that our expected E of x minus mu is the mean of the differences between each x and the mean. So that's going to be a bit tricky to visualize, but hopefully this graph might suffice. Imagine I draw this graph here, and the outcomes that we could get are 1, 2, 3, 4, 5, and 6, and we expect to get 3.5. That's not very straight, but you get the point. So my first roll might be a 6, my second roll might be a 4, my third roll might be a 2, my fourth roll might be a 3, my fifth roll might be a 5, sixth roll might be a 6, etc. The expected x is the mean mu, then the expected x minus mu is our expected mean, or expected difference between the mean and each data point. X minus the mean will give us that gap. And so it's an average of those gaps. And the expected x minus mu squared, well, what that does is it averages these gaps, but it squares them as well, and that has a really nice benefit. And that benefit is that while it does nothing to this first orange one, or really the second orange one, it makes this third orange one positive. Because if we add all those gaps together, they should equal 0, because that is the idea of the mean. The mean is the center, and it averages those gaps out to make it as close to the center as possible. But by squaring it, we're making them all positive. So what we can do with all these positive values is once we've squared them, made them all positive, we can take the square root of that. We can add them all together, divide by how many there are, and then take the square root. And that gives us a representation of our spread, our average spread, basically. And so you see that's what's happening up here. So we do, for each data point, x minus the mean, square it, sum it, divide by how many there are, and then take a square root. That square root cancels out the squaring to get the standard deviation. We don't take the square root for variance because standard deviation equals the square root of variance. So we have here, this is what you need to consider, that we know how to do the expected x, but if we actually work out the expected x minus mu squared, that means something that's really quite helpful. If we get variance is equal to that, well, variance is equal to the expected x minus mu squared, because the expected x minus mu squared is going to be our average difference squared. And then we can break that down using our expected value formula to get this. And that's how we can calculate our variance. And we don't have to worry too much about standard deviation if we know how to do variance, because if we're asked for standard deviation, you should always think instantly square root of variance. Determine the variance, take the square root. So just like before, with the only difference being that instead of having x times p of x equals x, we're going to have x minus mu squared times p of x minus x. Let's do our calculation. We already know that mu is 3.5. So if I do x minus 3.5 first, I get negative 2.5, negative 1.5, negative 0.5, 0.5, 1.5, and 2.5. And then I can square those. I get 6.25, 2.25, 0.25, 0.25, 2.25, and 6.25. And the variance is going to be the sum of those squares divided by m, but in this case we're working with this formula. So it's going to be the sum of x minus mu squared times the probability x. So I need to do that timesing the probability. So I'll just add that extra line in here. So I get x minus 3.5 squared times the probability x equals x. And this is a uniform distribution, so it's a bit boring at the moment, but I get 6.25 over 6, 2.25 over 6. There's a couple of decimal points in there. Trying to keep it small. 0.25 over 6, 25 over 6, 2.25 over 6, 6.25 over 6. I've got that illegal decimal happening inside a fraction, but it's part way to a question, so it's not the end of the world at the moment. And the variance is just the sum of all those. So that is 6.25 plus 2.25 is 8.5, plus 0.25 is 8.75. It's symmetrical, so it's double 8.75, which is 17.5 over 6. And we can write that down as probably best 35 over 12, just doubling it so we don't have any decimals. And of course the standard deviation is therefore the square root of 35 over 12. I don't actually have a calculator on me, but the variance in this case is about 2.9 something. So it's slightly under 3, because 36 over 12 would be slightly under 3. And that means that the standard deviation in this case is about 1.7. But that's not perfect, that's just me working out in my head. So just keep that in mind. And so that's a representation of how spread it is. The standard deviation and variance don't do a lot on their own, but if you're comparing two sets, they're really great measures to compare which one's more spread out. And example 2, in a fair game, I get to choose one cup. The following prizes exist. It's the same as before. What is the variance of the outcomes? Well, I've already done the expected value. So we had before set up x is 5, 2, or 0. And my probability that x equals x was equal to 1/10, 2/10, or 7/10. And my expected value, you'll recall, which we calculated earlier, was 0.9. So now I'm going to calculate x minus mu, my expected value, is 4.1, 1.1, and negative 0.9. And then I'm going to square that. And this gives me 16 point, and I'm doing this in my head, poor planning here, but I'm going to say 8.1. And then 1.1 squared is 1.21, and 0.9 squared is 0.81. and then I'm going to multiply those by my probabilities. So I get x minus mu squared times p of x equals little x, and that gives me 1.681, 0.242 and 0. And then my variance is the sum of all those, which is great because that zero's cancelled out one of them, and I get 1.923. And of course my standard deviation is the square root of that, which I dare not do in my head, but I'm sure that you could throw it into a calculator and work it out, and it should be about 1.4, maybe a touch less. So there's my variance and standard deviation of this set of information. Again, not overly helpful in this case, but just keep in mind if you had, say, 2 fair games, you wanted to work out which one had more variability, which one was more likely to give you consistent results. This is where the variance and standard deviation come in. Now, there is some other examples attached to the end of this, so I'm going to break this up into 2 videos, and I'll go through the other relevant relationships in another video. All the best.